Hi guys, welcome. This is week 4. We're wrapping up our first unit of semester 2. Let's take a look. This week we're doing lesson 89 and 90, which will be the last unit that we'll get into the review. So we'll jump right into it. So lesson 89, solving problems with two unknowns by graphing. So if we have what looks like a linear equation, we have x plus y equals 6, y equals x plus 10. And we can write these into a system of equations. Now this one is in standard form, this one is in y equals mx plus b form. So for graphing's sake, I would put them both in the same form, and I'll show you how we can do this on a calculator. So we put them into what's known as a system of equation, which is two or more equations with common variables. So since we have x and y, we can use these. We want to know where these two functions are going to cross, basically, where x and y are going to be the same. If they're linear, they're only going to cross in one place unless they're parallel, in which case they would never cross. Sorry. So if this is the one we're looking at, x plus y equals 6. Y equals x plus 10. So what I said is I would put them in both, since we can graph in our calculator, y equals form. Okay, let's look at this top one. Subtract x from both sides. Excuse me, y equals now negative x, positive 6 or plus 6, and then we have this one down here still. Now that we have them in y equals mx plus b form, these are both lines. This isn't going to apply for only lines. You can have functions that cross 2 or 3 times depending on their shapes. Let's take a look. So we're going to go into our calculator. Y equals. If you're ever getting an error message or whatever, just make sure these are turned off. If they're highlighted like that and you're graphing something and you get an error, that doesn't mean you're doing something wrong or it's impossible or anything like that. We just need to clear it out. So we had negative x plus 6, and then y equals x plus 10. Okay, then we graph. All right. So what's nice about these newer ones, if you have the yellow ones, it may just be a gray scale, but we can still see that they're crossing, even if they're colored or not. We can see that they have an intersecting point. Now what we can do is we can go second calc or second trace, this button right here. That's going to bring up this menu. We're going to go down to option 5. We want to find where they intersect. Now it'll say first curve, second curve, and then it'll say guess. I don't know exactly what language is behind that, but yes, we want first curve, enter, second curve, it's on our other function, hit enter, it says guess, yes, hit enter, and then it will show us where the intersection is. So these two lines cross where x equals negative 2 and y equals 8. So that's the only point that they are going to cross. And so we've solved our system of equations where x equals 2 and y equals 8. Then these two equations are equal. So we've seen that with, like, what do they use? Like Yanis, Sandra, or some. They always use x and y names on the test. We've seen some of those where they're thinking of two numbers. And we always have the trial and error method, but that can take a really long time. You know, there's really infinite numbers that can add up to be 6 when we start including negative numbers and decimal numbers and things like that. So it's a lot easier if we can come up with a simpler way and a faster way. And we can do that by graphing both of them and then seeing where they cross. And that's got to be the one point that solves that system of equations. Okay. Practice set, we'll go over those together. I guess just one example. Okay, and then lesson 90, we're looking at sets. And we're going to have a video that we watch with this. We have sets. They're indicated using braces. Again, the dots indicate that's continuing on to the left, as further from the origin in the negative direction. Dots to the right, it's getting further towards the positive. So we've already talked about sets of numbers with like whole numbers, 0, 1, 2, 3, counting numbers, integers, counting or whole numbers and their opposites, 0, 1, 2, 3. We have prime numbers, composite numbers, rational numbers, irrational numbers. We even have real and imaginary numbers, which is way down the road that we don't want to get into right now. But how we do this, there's a lot of different symbols and things that go with this. So we'll watch a video in class that goes over it as well. But just pay attention to some of them. So we use the set notation to denote the 7 even integers. Sorry. Set of even integers. Yeah. Okay. So that's what we're doing. So to indicate an element of a set, we use a symbol like a curved E. Okay, so E like element. 3 is an element of the set of integers. 1/2, it's now got the line through it because 1/2 is not an integer. It's not one of our whole numbers or its opposites. So it's not an element of the set of integers. Use set notation. So this is one of our symbols that we need to know, an element. Use set notation to indicate whether each number is an element of the set of rational numbers. So 2, yeah, that's rational. So we use this symbol. It is an element of the rational numbers. 1/2, yeah, it's not an integer or a counting number or anything, but it's still rational because it'll be expressed as a fraction. So again, it's rational if it can be expressed as a fraction or if it has a decimal number that repeats or terminates. If it's never repeating or terminating as a decimal, we can't express it as a fraction, then it's irrational, like the square root of 2. We do that in our calculator. It'll take it out to 9 decimal places, but that's because our calculator is set for that. It actually is irrational and continues on forever, just like pi. And actually, any square of any number that's not a perfect square, square root of 2, square root of 3, square root of 5, square root of 6, those are all irrational numbers. Okay. Graph elements of each on the number line. So again, it wouldn't be exact because the decimal number goes on forever. Square root of 1, square root of 2, square root of 3, square root of 4 is 2, so we know all of these are between 1 and 2. Okay. The set of integers, if we're graphing those for A, sorry, here we have 0, 1, 2, 3, 4, continuing on, and their opposites. So -1, -2, -3, -4. Now that one pay attention to because we're just doing the closed dots on each integer. We can't use a line connecting all of them up above like when we've done solving inequalities, like x is greater than 7, we'll put the open circle, or x is greater than or equal to 7, and use the closed circle and put an arrow to the right. We can't do that for this example because if we connect the dot, well, 1/2 right there would be included in many other numbers, and 1/2 is not an integer. So that's why we don't have a line connecting all of them, or just doing a shaded dot and then pointing to the right or the left. And it's not including all the numbers on here. It's just these values. Okay, subset, again, A is a subset of B. We would use this symbol right here. So it's kind of like our U. Now turn on its side. So an example of that, rectangles are a subset of quadrilaterals. So all rectangles are quadrilaterals, but not all quadrilaterals are rectangles. And so you kind of have to think about this. Use a subset symbol to show the relationship between the set of natural numbers and the set of integers. Okay, so lesson 1, natural numbers are the numbers we say when we count. So counting numbers, counting the natural numbers is 1, 2, 3, 4, 5. And so, and integers are 0, 1, 2, 3, 4, 5, and their opposites. So all counting numbers or natural numbers are integers, but not all integers are counting numbers. Again, the direction we read them does matter. Some of the symbols we use, draw in perfectly if you want to just use capital N or shaded in, whatever, that's natural. Counting numbers, this Z is integers. The Q is for rational numbers because they have quotients. We can write them as fractions. Real numbers, capital R. Another way we can compare things is using a Venn diagram. I know we use these a lot in language arts. And we can also use them in mathematics. So a Venn diagram of something's a subset, it's inside. We can also have an intersection where A, and then I just remember this by N, intersection, because it's the N, so A and B, the intersection of A and B. Okay, so rectangles and rhombuses. Okay, rectangle is a four-sided shape, and then a square is a special four-sided shape. All the angles are right angles, and all the side lengths are equal. Whereas rectangles, the sides don't have to be equal. But squares are a form of rectangles, and a subset of them. And a square is also a subset of a rhombus, because a rhombus is a parallelogram. A square is a parallelogram, and all the sides are the same. So this is an intersection between rectangles and rhombuses, or squares. Union is where we're joining A and B, or whatever we're talking about. So U for union, N for intersection. Again, a lot of symbols we'll go over more in class. A union, if we're including A and B. So sets A and B are shown below. Find A, and then intersection, because N, so the intersection of A and B, well, 1, we don't have 1. 2, we do have 2, so 2 would be 1 of them. 3, no, 3. 4, okay, we do have 4. So 2 and 4 are the intersection, the only ones that they have in common. Now, if we're talking about union, where we're bringing them together, well, then we have 1, 2, 3, 4, 6, and 8. We don't have to write 2 and twice, because it's not like a number on a line or taking average or anything like that where we need to account for 2 of the numbers. It's just 1, 1, 2, and 2, so we just write 2 once. 3, 4, even though it's in both sets, 4 is included in it. 6 and 8. So that's the union, intersection and union. Now, empty set, we use this circle with a line through it. We use that down the road also if we have something that's undefined, like we get an equation and we're trying to solve for x and we end up having to divide by 0. We can't do that, so we say it's undefined, or we put a circle with a line through it. We can use that same symbol for an empty set. But if there are no elements in the intersection of two sets, we say the intersection is an empty set. So like the intersection of odd and even numbers. Well, you're either odd or even. You can't be both, so that would be an empty set. There's going to be no intersection between those. Okay, there's a breakdown of the symbols. The set, E element, kind of that trident or whatever, that E looking thing. Subset, it kind of looks like a C. N, intersection, U, union, and then this undefined symbol if it's an empty set. Okay. Venn diagram, we have 1, 2, and 3, and then the natural numbers are counting numbers. Well, 1, 2, and 3, the set of 1, 2, and 3 are part of our natural numbers, but the natural numbers go beyond that. 1, 2, 3, 4, 5, 6, and so on. So A would be a subset of N. Okay, we're trying to find where A and B intersect. So 2, 4, 6, 2, 4, 6, 1, 3, 5. No numbers in common, so there is no intersection, so we use that empty set symbol. All right, and we will go over these practice set problems. Again, we'll watch a video on this. It's not super entertaining or anything, but it's kind of good to break down the different symbols and when we use them, and some other examples that we use. I mean, it's more than just numbers. We can use these, all of these when we're talking about language or biology or things in nature or whatever. We can say that this is a classification or subset of this, or this has no relationship with that, or if we combine, there's all different sorts of things that we can do with that. So we'll look at these when we return. That's all we have. I'll see you guys in class.